Well, I will now start with the second section about Newtonian mechanics. And of course I will start with Newton's laws as they appeared here on the original form in 1687 in Latin, and they should be learned by heart before the end of the course. So, translated to English, this is what it gives. And first law of Newton says that if no force is acting on an object, then if the object is at rest, it will remain at rest. And if the object is in motion, it will keep its speed and its direction. Yeah? The second law says that if there is a change in motion, it is proportional to the applied force and in the direction of this force. The third law says that the mutual action of two bodies on each other are equal and opposite in directions. Well, first, an element of vocabulary, what is called velocity. V with an arrow is a vector quantity, so it has a notion of direction, whereas speed is a scalar quantity, and it's actually the magnitude of the velocity vector. Well, suppose now that you have an elementary mass m traveling at velocity v. Well, you can give it what is called a linear momentum. This is a vector p, which is the mass times the velocity vector. And what the second law of Newton says is that if there is a change in momentum, it is equal to the net force acting on the mass. Okay, so now let's have a look at this variation of linear momentum. You have the product of two things here, mass and velocity. So if you take the derivatives, you will have two terms, one involving the derivative of velocity. This will give you mass times acceleration vector, but you also have a term that is related to the variation of the mass. In lots of applications, but not all, this term is zero because the mass is constant. If the mass is constant, you obtain the well-known equation which states that mass times acceleration equals force. Don't forget that this equation has to be seen as a vector equation. The first law of Newton can be seen as an application of the second law. This is why I started here with the second law. If there is no force acting on the mass, it means that mass times the acceleration vector is zero, which means that the acceleration vector is zero, or that the variation in speed is zero, which is equivalent. Consequently, as I said before, if an object is at rest, it will stay at rest, okay? And an object, if it is in motion, it will not change its velocity vector, so it will have the same speed in the same direction. Well, we go now to the third law of Newton, and here you see that there are two bodies that are exerting a force on one another. You have this force here, it's the force of body 1 on body 2, and this is the force that's exerted by body 2 on body 1. And Newton's third law just says that these forces are equal in magnitude but opposite in direction. Okay, Newton's third law also says that a single isolated force cannot exist. And also note that the action force and the reaction force, as they are called, act on different bodies. A word of caution. The laws of Newton hold for objects which are ideal. This is why we talked about elementary masses. These are single point masses or particles. If you go to more involved bodies, rigid bodies, which are a collection of particles, you need something more complicated, and these laws of motion will be introduced later on in the course. They are called Euler's laws of motion. A second word of caution is that Newton's laws, as we will see in the next few slides, are valid only if you work in a inertial reference frame or in a Newtonian reference frame. Well, you're all familiar with the concept of a reference frame. There are some frames which are stationary in space, fixed in space, or moving at a constant velocity. This means that the speed remains constant, there is no acceleration, and there is also no change in direction of the velocity. Those frames, those reference frames, are called Newtonian or inertial. And if you describe the motion of a system in such a frame, you only have to look for forces that are inside the system. If you work with non-inertial frames, we'll see that you have to work with fictitious forces, and these fictitious forces have their origin outside of the system. In this course, right-handed coordinate frames are used. This means that you need to use your right hand, and for instance you take your thumb and you point it in the direction of the z-axis. You look then at the curl of the fingers, and they represent a motion from x to y. Okay, so viewed from the z-axis, the rotation movement from x to y is seen as positive, and you will see that it is counterclockwise. You can do something similar when you point your thumb in the x direction, then the natural rotation is y to z, and this is then the rotation movement that is defined as positive, and again it is counterclockwise. You can do something similar in the y direction, and there the natural movement is z to x, which is again defined as positive and counterclockwise. In this slide we do a rotation around the z-axis, so we go from a frame x, y, z to a frame x prime, y prime, z prime through what is called an Euler rotation. As you can see, the z-axis is sticking out of the screen. Okay, so if you take the right hand and you point it in the direction of z, you will see that going from x, y to x prime, y prime is defined as positive and counterclockwise. So if you have a point P that is described in the original reference frame, and you ask yourself how you're going to express it in the new reference frame, well, you'll obtain its coordinates P prime by simply using a rotation matrix and use the equation that is given over here. Okay, this kind of rotation matrix here is something that you have encountered in the course of linear algebra, and you know that it is an orthogonal matrix because the rotation preserves distances and preserves angles. Well, we've seen that the rotation matrix, when you turn around the z-axis, is rz theta. This is what we've seen in the previous slide. Of course, you can turn around the x-axis, then you have this rotation matrix, or around the y-axis, then you have this matrix. Okay, well, let us see if we can find this rotation matrix. Okay, so remember we are turning around the y-axis, and in our case the y-axis will be pointing towards you, outside of the screen. So this is the z-axis, this is the x-axis, and you see that if you take your right hand, you point it in the direction of y, then a positive counterclockwise rotation is one from z to x. So now, if we take the orders of the variables to be z, x and y. Then we know from the previous slide that the rotation matrix, now we'll call it ry hat because the order of the coordinates is different here, will be cosine theta, then sine theta, 0, here 1, all zeros, and here you'll have minus sine theta, and here you'll have cosine theta. Okay, so this is the rotation matrix if you have this order of the variables. Of course you have to reorder them to have the coordinates x, y, z, and if you do that you'll obtain this rotation matrix. Okay, inertial frames, or Newtonian frames as they are called, are easier to use when compared with non-inertial frames because they have physics whose causes lie inside the system. If you're using non-inertial frames, then they have physics whose causes lie outside the system, and you have to use these fictitious forces or inertial forces. A reference frame can become non-inertial for essentially two reasons. For instance, it can be a rotating reference frame and then the velocity vector is changing direction, or it can be accelerating, and in that case the velocity vector is changing magnitude. But these non-inertial frames can be used, and we will see in the next slide how Newton's law, Newton's second law, can be adapted, and this adaptation actually causes the appearance of fictitious forces or inertial forces. We'll first consider the case of a non-inertial frame, but one that is accelerated in a straight line. So you have two frames here. You have the frame x1, y1, okay, x1, y1, which is inertial because it's linked to the Earth. Then you have a second frame which is non-inertial. It's linked to the car that you're seeing here. So x2, y2. Since the car is accelerating and the frame is linked to the car, of course the frame becomes non-inertial. Okay, so we have a mass here and it's subjected to a force, and the easiest thing to do is to describe it in the inertial frame, because we know that in the inertial frame Newton's laws are valid, and so we'll write the second law of Newton for both components x and y. So it's kind of easy. Mass times acceleration in x direction is equal to the x component on F. You have something similar for the y component, and of course here you have an additional term that takes into account gravity. Okay, now we can see how the two frames, the inertial one and the non-inertial one, are linked. This is very easy because you know that the non-inertial frame is subject to an acceleration ax. Okay, so we'll make the assumption that they started both at the same spot, and that there is some kind of initial condition for speed. And if you do that, if you integrate twice, well, you have the relation between the x1 component and the x2 component. Okay, so x1 is the coordinate of the mass in the inertial frame, and x2 is the coordinate of the mass in the non-inertial frame. The relation between y1 and y2 is kind of obvious. So now what we can do is take this relation, differentiate it twice, and substitute it in this equation here. We have to differentiate twice because you have x1 dot dot and y1 double dot. If you do that, you obtain this equation. Okay, so you can see that nothing has changed for the second equation, but for the first equation you obtain something different than you had in the inertial frame. So you have mass times acceleration in this non-inertial frame, then you have the force that is acting on the mass, and there is this term that is appearing, which is a fictitious force. It comes from outside the reference frame. You can see that here. And you see that if you want to write the second law of Newton in this non-inertial frame, you have to account for a fictitious backward force, a backward acceleration force minus max. If you do that, you can write the second law of Newton, but again it uses this fictitious backward force. Okay, let's see what happens with rotating frames. So we have two frames here, one which is inertial, xyz in uppercase, so it's a fixed frame, and then you have another frame which is rotating, right? And it's called xyz lowercase, and the z-axis lowercase z and the z-axis uppercase z are in common. You also see that the origin of the two frames is the same, right? We've said that this frame is inertial, this one is rotating, which says that it's non-inertial. So we are now interested in linking the two frames. So we'll write the unit vectors of the rotating frame. Of course we are interested in the unit vectors x and y of the rotating frame, and we'll write them as a function of the vectors, the unit vectors again, but this time in the inertial frame. So this is why we have a capital X here and a capital Y. You have something similar for the unit vector Y in the rotating frame. So now we'll be interested in seeing what happens if we take the time derivative of this thing here. Here we have the product of two things, so if we take the time derivative, you expect two terms. The time derivative of this one will give you this thing here times the unit vector with capital X, and then you would also need to take the derivative of this one, but this is a fixed vector, so it will not give any contribution. Okay, so this means if you take the time derivative of this one, you obtain that, and if you take the time derivative of this one, you obtain this thing here. You see that each time you have a theta dot, theta dot, theta dot, theta dot, so you can take it up front, and you will see that what is left behind, if you take the theta dot up front, is this thing here. So the time derivative of this unit vector x in the rotating frame is given here, and you have something similar for the time derivative of the unit vector y in the rotating frame. Okay, so if we're looking at this and you look at this vector here, and you'll see and you want to see how it's changing, you will see that it will be changing in the y direction. This is exactly what is written here, and this one here, if it's changing, it will be changing in this direction, and this is changing in the opposite direction to the unit vector x in the rotating frame. Okay, what you see here is the result from the previous slide that we'll be using here in this slide. Again, you see the two reference frames, the one that is inertial and the other one that is non-inertial, that is rotating. So this one with the lower x, y and z is the rotating frame, so it's non-inertial, right? So now we'll take a mass, okay, and we'll have its position vector, which is vector r, and we'll describe it in the non-inertial frame, and we'll describe it in this way. Okay, now we can take the time derivative of this vector and see what's happening. So if we take the time derivative of this term here, since it's the product of two things, we have to take time derivative of this one times the unit vector in the x direction in the rotating frame plus rx times the derivative of this one, right? So the two terms that I've mentioned are this one and this one. Of course, you'll do the same thing for this term and for this term, and this will be generating this term, this term, this term, and this term. Okay, there is a term that is equal to 0 because this term is fixed, right? So now we can rewrite things in this way, because what we'll be using, of course, is that this one here, well, you'll find it over here, so it's equal to this thing, and the derivative of the unit vector lowercase y in the rotating frame, well, it's equal to this thing here. So if you plug it in into this equation, this is what you obtain, right? And the last term, well, that can be seen as a cross product of two vectors. The first vector is the angular velocity vector, right? And this is pointing in the z direction. Yeah, it depends on the velocity, speed, right? Theta dot. And another vector, which is the original position vector. Okay, how can you see this? Well, you can write this cross product as a determinant okay, and then you put 0 0 theta dot, and you put rx, ry, rz, and as you're specialists of computing determinants after the course of linear algebra, you will see that this is giving this thing here, right? So what have we shown? We have seen that the velocity vector in the inertial frame can be written also into the non-inertial reference frame, and then you need this thing here. This is the velocity vector in the rotating, R is for rotating and F for frame, and you need to add a term that comes from this cross product. So this is the equation that we've shown in the previous slide. Yeah, remember that you have an inertial frame it's x, y, z in capital letters, and there is a rotating frame, non-inertial, x, y, z in lowercase letters. The vector r here is expressed in the rotating frame. It's the position vector, and in general this equation holds for any axis of rotation. So you have two sides of the equation. The left side, there is only one term, and that's the velocity vector expressed in the inertial frame, right? On the right side you have two terms. The first term is the velocity vector expressed in the rotating frame, and remember that this rotating frame is turning with an angular velocity that is expressed by a vector, and this vector is directed in the z direction, right? And so you have a rotation like this. You have a second term here, and that accounts for the relative motion of the axis. So how can we give an interpretation of this? Well, I think the easiest way to do that is to say, for instance, that the mass is fixed in the inertial frame, right? If it's fixed in the inertial frame, this means that the velocity in the inertial frame is 0, and the only way to have a 0 in this second side of the equation is to say that the velocity in the reference frame is simply the cross product of minus omega cross position vector r. Yeah, so what does this mean? This means that if the mass is fixed in the inertial frame, then the mass will be appearing to be rotating backwards with angular velocity minus omega, which is kind of logical. Okay, this is the equation that we have obtained in the previous slides, and we would like to obtain something similar, but not with the velocity in the inertial frame, but with the acceleration, right? Just a reminder, the r is the position vector in the reference frame. So this thing here, you can see it as the derivative of the vector r with respect to time, but seen from the inertial frame. Okay, so what I've done over here, and so this is the result of the previous slide. Well, you can do something similar if you're interested in the derivative of the velocity vector in the rotating frame. If you're interested in its derivative, time derivative, seen from the inertial frame. So what will I have? I will use this equation here. Yeah, well, I'll have not the velocity but the acceleration in the rotating frame plus omega, the velocity vector, cross this one, the velocity in the rotating frame. Okay, so these will be two equations here that I will be using later. So now I need to do the time derivative here as seen from the inertial frame, and this will produce me the acceleration in the inertial frame. So time derivative of this one with respect to the inertial frame, this is this one. When I will be taking the time derivative of this one, it will produce two terms, this one and this one. So derivative of this one, there you have it, cross product with position vector r, and then another term with omega, cross product with the time derivative of this one, with respect to the inertial frame. These quantities here and these here are the ones that have prepared. This one is the one that you've got here, and this one is the one that you've got over here. So now you can start injecting this thing here at this spot here, yes, and this thing here you can inject it over here. And now it's just a question of expanding things. Then you will see that this term here and this thing term here will be appearing 2 times. This thing here, well, we'll write it slightly differently. Instead of saying that's the derivative of the velocity rotation vector, we'll say that it's alpha, which will be the acceleration rotation vector. Okay, but this thing here is exactly what you see over here, and this one here cross this thing here will give you this term here with a triple cross product. And of course you have the acceleration in the rotating frame. So we obtain now this equation, which expresses the acceleration in the inertial frame as the acceleration in the rotation frame plus 3 extra terms that are appearing over here. We have just shown that the acceleration vector in the inertial frame can be written as a function of the acceleration vector in the rotating frame plus 3 additional terms. What we know is that the second law of Newton is valid in an inertial frame. So we can write that the mass times the acceleration vector in the inertial frame is equal to the net force. If we chose to work in a rotating frame, then we have to adapt our equation. So we are going to replace the acceleration in the inertial frame by what we have here on the right hand side of the equation, and this is what we obtain. So we can see that we can write something like this equation here, which is mass times acceleration vector now in the rotating frame, okay, is equal to the sum of the forces, but of course it will involve the applied external forces, and there will be 3 additional fictitious forces appearing. Okay, this is a term, another term, and another term. We'll see how we'll name them in the next slide. Okay, remember that omega is the angular rotation of the frame, pointing in the direction of the axis of rotation. Alpha, the vector alpha, is the angular acceleration. The vector r locates the elementary mass in the rotating frame, and the velocity in the rotating frame is the speed in the rotating frame. So it's the speed according to a rotating observer. We've just seen that you can write the second law of Newton in a rotating frame, in a non-inertial frame, if you take into account fictitious forces. So you can write mass times acceleration vector in the rotating frame is equal to the sum of all forces, but you have to take into account the external forces and 3 terms, the first term, second term, and third term. The first term is the Coriolis force, the second term is the centrifugal force, and there is a third term that is called the Euler force. This third term only appears when there is acceleration in rotation, and in many applications the acceleration is either 0 or it's small. So in a lot of applications you will see that this third term can be neglected. Well, let's first have a look at the Coriolis force. Now remember, it's a fictitious force, and for that we'll draw a merry-go-round, okay, which is rotating around an axis that is sticking out of the screen at an angular speed omega, right? And the idea is that we have an observer which is sitting on the merry-go-round and is sitting over here, and he will be throwing a ball, right? And we'll try to see what happens in a inertial frame, which is a fixed frame that is fixed to the ground, okay? Inertial frame. And then we'll take a non-inertial frame, and it's a frame that is fixed to the merry-go-round, right? And it's turning with angular velocity, right? Remember that the Coriolis term is minus 2m, and then you have to take the rotation vector. Remember that this is the vector that is sticking out of the page, cross product with the velocity vector in the rotating frame. So we'll first have a look at what's happening in the inertial frame, right? And if the observer is throwing the ball, well, it will go like that in a straight line. So this is the trajectory seen by someone in the inertial frame, for instance, looking from above, right? Well, the direction of velocity in the rotating frame is this direction. The vector of rotation is sticking out of the page, so the Coriolis force will be perpendicular to the rotation axis and the velocity vector in the rotating frame. So it will be pointing out in this direction, right? Because you know, you can imagine that the observer, which is sitting on the non-inertial frame, he will see a quite different trajectory, right? He will see something like this. So from the point of view of the observer, which is sitting on the non-inertial frame, it's as if a fictitious force is acting on the mass and making it go in this direction. So what I will be showing now is a nice video from the from the MIT that is explaining Coriolis effect. You can find it on YouTube. So as you can see now, they're sitting on an inertial frame and throwing the ball, so the ball is going in a straight line. So now the reference frame has become non-inertial, and you can see that there is the Coriolis effect appearing. Yeah, the camera is mounted on the ground, fixed to the ground. And as you can see, the ball is going in a straight line. Yeah, so Newton's law can be applied. Now you have a rotating frame, the camera is mounted on the rotating platform, and now you should account for this fictitious force that is called the Coriolis force. Well, let us have a look now at the centrifugal force. So the best example of that is a stone attached on a string, and you make this stone term. Let's try to draw this. So you have your stone over here, its mass is there, the center is over here, and let's draw the axis of rotation. We'll call it omega. So this distance here will be r, and the position vector is r, right? So remember that the Coriolis force is minus mass, then rotation vector cross product with the same rotation vector across the position vector. Yeah. So if we take this one and you make this cross product, you will see that this thing here is pointing in this direction. So this is omega cross product with r, right? And now if you make the cross product of the triple cross product, you will have your vector sticking out over here. This will be omega, right? And the triple cross product will be pointing inwards, but of course you have the minus sign over here, so the centrifugal force Fc will be pointing outwards, and it's a radial force. Okay, so Fc is a radial force, it's pointing in this direction. And if you want to see what its magnitude is, right, so you have here something that is turning at radial rotation speed omega. Well, you have m, and then you have to multiply by the square of the rotation speed, and you have to multiply by r, which is this distance here. So if you want now to use the tangent speed, we'll call it v, you know that v is equal to omega r. So omega is v over r, and you can stick it in the previous formula, and you obtain m is v squared over r.